Hi everyone, so today we're going to continue our discussion on functions, and we're going to specifically focus on functions that satisfy some additional conditions. So these special kinds of functions, they're called injections or one-to-one functions, surjections, which are also called onto functions, and bijections, which are sometimes called one-to-one correspondences, but most of the time we'll probably call that one bijection. Okay, so first let's look at injective functions. So the definition for this is we say that a function from f from a to b is one-to-one or injective if it satisfies this universal condition. So it says if you give me two elements in A, any two elements, so for all a1 and a2 in A, if those two elements are distinct, meaning that they're not equal, then their outputs have to be distinct. So in other words, in injective functions, you're going to, if two things are not the same, then their outputs will not be the same. So distinct elements map to distinct elements. Now, when it comes to proving something is an injective function, the best approach is really not to use this original definition, but instead take the contrapositive. So if I take the contrapositive of this instead, you will get this universal statement. So for all a1 and a2 in A, if f of a1 is equal to f of a2, then a1 is equal to a2. So notice we're just you have this if then, and the contrapositive, you're going to flip these two and then negate them. So the nice thing about this contrapositive version is that in terms of proving it directly, you'll be dealing with equalities rather than inequalities or non-equalities, not as you would in the original definition. The original definition is more intuitive in a sense, though, because this is saying distinct things map to distinct things. Okay. So let's write out the template for proving something is an injective function. So the template for that, so template. For proving f from a to b is one-to-one or an injective function, is injective. Okay, so the proof, just kind of following what we set up above, if we approach this using the contrapositive technique, then we would want to prove this universal statement. So you want to show for all a1 and a2 in A, so you'll let a1 and a2 be in A, and then we're going to show this if then, which means if we're doing this directly, you're going to suppose the if part and show the then. So suppose f of a1 is equal to f of a2, and now you have this equation, and then what you want to do is you're going to show me that a1 is equal to a2. So somehow from this equation, we're going to deduce that a1 is equal to a2. So you'll do a bunch of work here, and you will eventually get a1 is equal to a2, and then that's exactly what we want to show, so we'll be done. So this is your proof template, okay? Now, just to be a little bit more clear, let's explore this a little bit more. So let f be a function from a to b. If we say the function f is an injection or injective, then that means that it satisfies those two universal statements that we had above. But what about the negation? So the negation, we have to be a little bit careful, right? Because the negation, so the function f is not an injection would mean, well, you have to negate this universal statement. So the for all becomes there exists, so there would exist a1 and a2 and A, and then we actually would have an and statement here, because the original one is an if then, right? And just recall that if you have an implication, so just recall, if you have P implies Q, this is logically equivalent to not P or Q, right? So what would the negation of this be? Well, the negation would be logically equivalent to the negation of this, which would be, by De Morgan's law, it would be P and not Q. Okay? So when you're negating an if-then, you should write this as an and statement. There's no trivial way to rewrite that negation in terms of an if-then. So you want to use this approach. And that's exactly what we're doing here, right? So we actually have the original P as the same. So A1 is distinct from A2. A1 is not equal to A2. And the negation of Q, which would be that the two outputs are the same. So if you think about this intuitively, remember we said an injective function, if you give me two distinct elements, right, then their outputs are distinct. So distinct elements map to distinct elements. But what would the negation of that be? Well, you would have distinct elements, and then their outputs would actually be the same. So if you wanted to draw kind of like a little picture for this, okay, do you see that A1 is here, A2 is here in A, and over here is B, and these two are distinct from each other, right? So A1 is not equal to A2, and so their outputs, which is f of A1 and f of A2, they actually have to be distinct from each other. They can't go to the same thing. Yeah, so this is what an injective function would look like. You could have some extra leftover elements of B that are not hit with an arbitrary injective function. So the picture for this guy, if the thing is not injective, look at what we're saying. We're saying that there actually does exist an A1 and an A2, okay, in A, and they're not equal, so they're distinct from each other, but then their outputs are the same. So the picture for that would look like this. So A1 would map here, which is, and we can call that f of A1, and A2 would map to that same thing. So you see, from our original intuition, you have distinct things mapping to the same thing. So this would not be an injection. Okay, so this picture is not an injection, right? And this is the picture for an injection, right? Distinct maps to distinct. Okay, so if you ever see this kind of picture, you would know that the function is not one-to-one or an injection. Of course, you could have some other things here. The other thing, one thing I should point out is if you pick any other pair, it may actually look like this for other pairs, but you're just saying that it fails the original universal statement, which is saying you can exhibit an example of two things that happen to have the same output. And then over here, everything in A, no matter what pair I pick, the picture kind of has to look like that. So just keep in mind this universal statement versus this existential statement. Okay, now moving on to another kind of function, a onto function. So a function f from a to b we say is onto or surjective or a surjection. So that's another way to say it. If the range of the function is actually equal to the entire codomain. So remember, the range is the collection of outputs, whereas the codomain B is where the outputs actually live. So we're actually saying the entire range is all of B. So nothing is missed, right? So so every single thing is actually hit. So if you kind of go back to our original picture for functions, remember that the range would be the image of A, right? So if you take if you actually mapped everything from A, there would be nothing missed. Okay, so the range of the function is actually the entire codomain. Okay, so this would be onto, and then something that would not be onto, the picture would look like something like this. You would have A and B, and then your range will always live in the codomain. Okay, so here you see that this is the range of your function, and what we're saying is there's actually some leftover elements here. So you see that there's some things in B that are actually not in the range of the function. So you would say this is not onto. Okay. Okay. How do you prove that something is onto, though? We should write out the template for that. Okay. So the template. Oh, sorry. First, I should tell you what the actual statement is. So formally, instead of saying that the range is equal to B, you would say it as this existential statement. So you would say, for every element B of the codomain, there exists an element A in big A such that f of A is equal to B. So in other words, what you're saying is, go back to this picture. You pick anything that you want in B, little b, and there should be an A over here that actually maps to this, and that is f of A. Okay, so no matter what you pick in the codomain, there should be something over here that gets mapped to it. So that's this idea of onto. You're guaranteeing that everything in B is an element of the range. Remember, the range is the collection of these outputs made by this function. Over here, you see these extra little elements that are not hit. There's nothing in A that's going to map to that, because this is the range. This is where all those elements go. They go inside that circle. Okay, so these are essentially missed by that function. Okay, now looking at this existential statement, how do we come up with a proof template? Well, proof template for showing f goes from A to B is onto. Okay, so staring at that existential statement at the top, how does this start out? Well, it starts out with a universal statement for all b, little b and b. So that's, you would just say let little b be an element of b. That's our assumption. And then what you're going to do is you're going to show that there actually exists, right? So you can write that if you want. You don't really need to, though. So show there exists an A and A such that f of A is equal to B. So you don't actually need to write this show part out. The next step in the template would be that you would exhibit an example of such an element. So let me write out how I usually write this. So I would say consider A equals something. Okay. Now we don't currently know what that is. All right. So just I would just leave a little blank here for just a second, and then you could say now, what is f of A? Well, f of A would be f of this blank. Okay. And you would simplify this, and eventually you would want that to actually be equal to B here. Okay, so kind of look at this template. So you're trying to show there exists a little a in the set A that'll map to this little b here. So we don't know what it is just quite yet, but we're going to try to find it. And if we find the right thing, then f of A will be eventually equal to B. So here's kind of your work here. So the work is actually to find this. So find this on some scrap paper. Okay, so over here, you're going to do some work. The reason I say you're going to do this on scrap paper is usually the technique to actually find this A is effectively illegitimate, because we're trying to force this to actually happen. All right, it's illegitimate in the sense that we can't just write this in our actual proof. But on scrap paper, what you can do is you could kind of say to yourself, all right, if I want this to be true, if I want f of A to be equal to B. All right, that's what I want. So on scrap paper, there's nothing stopping you from actually saying, well, what does this equation actually mean? And so what you can do is you can kind of solve for A here. And then this is actually what you're going to put up here. All right, so this is a little bit strange. And we're going to have to do a few of them to make sense of this. But the reason that I'm saying over here that this is on scrap paper is look at what we're actually doing. We're kind of assuming what we're proving, which is a huge no-no, right? You don't want to do that in an actual proof. We can't just assume f of a is equal to b. We're trying to show that. But again, we're also trying to exhibit an example. We're just trying to find an example of such an a. So you can do a little bit of scrap work. You can find out what that a is, and then you could say, oh, consider this a, and then go and calculate what is f of a. And of course, it should work if we actually can solve this on the scrap paper over here. All right. So I know that this organization is a little bit strange, but after we do a few of these, hopefully it'll make a little bit more sense. Okay, and just like we did with injective functions, let's look at what does it mean for a function to be a surjection, and what does it mean for a function to not be a surjection. All right, so the original definition, we could think of it in two different ways, right? So we say that a function is a surjection or an onto function, means that the range is equal to the codomain, and the codomain was B. And then another way to write that is using this nice universal statement. It's saying, give me anything in the codomain B, and show me that there is a little a that'll map to that element. Okay, that'll ensure that everything in B is actually in the range. So you're kind of confirming this. It's a more formal way of writing that first one. And then the second thing I want you to look at is, okay, well, what would it mean for a function to not be a surjection? So what that means is we could just negate this statement right here. Okay, so the negation of this would say there exists a B in B, and then the negation of this existence would say for all little a in A, and then you would want the negation of this equals, right? So that would mean that they're not equal. Okay, so now reading this, it says there exists an element of B such that for any little a in A, in other words, every element of A, you'll never have f of a equal to b. All right? So what that's saying, let me kind of draw a picture for this one. Okay? So a picture for something that is not a surjection. You would have this kind of picture. Well, I drew it up above, actually. I drew it up here. Right? So you see, you have these elements. Let me write it again down here. Okay, so you kind of have, here is the actual range. So here's A, here's B, and then here is our, we'll call this element our little b here. Okay, so so if you're claiming that it's not a surjection, I should have this picture. So there should exist something in the codomain, like this guy right here, such that there's nothing in A that maps to that. Everything in A maps into this circle here. Okay, every single element will map into that circle. But kind of this B element is not in this sort of inner circle, which is the range. Okay, this right here is the range of F. So you kind of see that the range is not all of the codomain because there's something in the codomain that's not actually hit. Right? So this would be an example of a function that is not a surjection. Now, if it is a surjection, you won't have this. You'll actually have that this inner circle is actually all of B, which is this first picture that I drew up here. Okay, so everything is hit. Okay, and then finally, bijective function is the simplest to explain out of those two because all that means a function is a bijective or bijection or a one-to-one correspondence if it's both one-to-one and onto. So to prove something's a bijection, you just prove that it's one-to-one and onto. Use both of these templates up above. Okay, so I don't need to explore this separately. Right? For something to be, if something is not a bijection, well then it fails one of those properties. It fails one-to-one or onto, because it has to be both. Okay? Okay, what I think might be a good idea is to maybe draw a picture for you just to illustrate the possibilities that you could have. Okay, now this would be for really small sets. Okay, so let's say for this example I have A and I have B. Okay, and let's just say that the set A only has two elements in it. Okay, you can label them with something if you want, but maybe let's just label them as these dots here. And then B, let's say that it has these two elements here. Okay, So A and B only have two elements in them, whatever they may be. And let's make a function, and let's say that the first element maps to this guy over here in B, and the second element of A maps to this guy over here. So this picture satisfies all the conditions. Do you see that it's 1 to 1 because distinct elements map to distinct elements? So this is a 1 to 1 function. You can write 1 to 1 like that, or you can write it out, right? Injection. Okay. And it's also onto because do you see that there's not missing elements over here? There's nothing. Everything in B is hit, right? There's only two elements of B, and both of them are hit by something in A. So the range is all of B. So this is also onto, which you could write surjection. All right. And so that means it's a bijection, right? Because it satisfies both of these conditions. So bijection. You could also call it a 1-to-1 correspondence, but I really don't like that terminology because I think sometimes you might think that it's a you might confuse it with just 1-to-1 function. So I'll probably exclusively use bijection or a bijective function. Okay, so this is kind of the nicest situation that you could be in. Well, what about other cases? Well, let's do an example of something that's 1-to-1 but not onto. Okay, so for that one, we'll have a set A and a set B again. But in this case, let's say that A has 2 elements, and let's say B has 3 elements. Okay, so if I actually draw almost the exact same picture, if I have the first one go into the first one, second one go into the second one, now look at this. This is actually still 1-to-1 because I still have distinct elements getting mapped to distinct things, right? These two are distinct and they are getting mapped to distinct things. However, do you notice that there's a problem with this function in that it is not onto because there's an element of B that's not hit, right? This third element is not hit by anything in A. So this is so this function is not onto. And of course, since it's not onto, it is not a bijection, right? So you can only have a bijection if it satisfies both of these. I mean, you could write not a bijection. Not a bijection. Okay. What else could we have? Well, we could have something that's onto but not 1-to-1. How would that look? Okay, so for this one, let's say that A has 3 elements and B has 2 elements. Okay, so let's have the first element mapped to the first one. Let's have the second one mapped to the second one of B. And let's have the third one also mapped to the second one. Now this is a perfectly fine function, right? Because to be a function, you just have to make sure that everything in the domain gets mapped to something over here in B. Okay, and so it's definitely not 1-to-1 though, because do you see that I have these 2 distinct elements over here and they're actually getting mapped to the same element. So distinct thing, I have an example of 2 elements that are distinct but they have the same output, which immediately tells you that it can't be 1-to-1. So this is not 1-to-1, but it is onto because everything in B is hit, right? The range is all of B, right? There's no element that's not hit. Okay, and since it's not 1-to-1, it's also not a bijection. Again, it can only be a bijection if it satisfies both of these conditions. All right, so what's the only other situation that we can have left? So here we had 1-to-1 and onto, here we had 1-to-1 and not onto, here we had not 1-to-1 and onto. So what could we make a function that's not 1-to-1 and also not onto? Well, sure. So here's A and here's B. Okay, so let's say A has 2 elements and let's say B has 2 elements. I can actually make an example with something quite small, right? So let's say that the two elements of A both map to this first element of B. So it's definitely not one-to-one for the same reason from the previous one, right? I have an example of two distinct elements that have the same output, so it's not one-to-one. It's also not onto, because there's an element of B that's not hit by this function, right? That's not in the range, okay? And then, of course, it's also not a bijection because it fails not only one, but it actually fails both of those things. Okay. So these are kind of like the four possibilities that you can have. I just wanted to give you a picture for each one for small sets. Okay. Now, in terms of actually proving things, these pictures just help you get a little bit of an intuition behind what these special kinds of functions look like, okay, in terms of when you have really simple sets. But in general, you're actually going to be given functions that satisfy some kind of algebraic definition, right? So this next example, let's say that I give you this function f, which goes from z to z. So that means that the inputs are integers and the outputs are integers, and it's defined in this way. So f of x is equal to x cubed. This is you're much more familiar with seeing functions like this. So I give you an algebraic rule. So you give me the input, and then I cube that input, and that'll be the output. All right? So it's definitely a function, right? If you give me an integer, and then I cube it, it's going to be an integer. So it's well defined for sure. But the question that I have for you is, is this function an injection? And then we'll ask the same thing, but about surjection. So is this function a surjection onto? And then once you tell me those two, you'll be able to tell me whether or not it's a bijection. Okay. So let's look back at our template, and is f an injection, a one-to-one function? Well, we don't know the answer quite yet, but we can attempt the proof, right? So proof for this, what would that look like? Okay, so remember the template up above, we pick two elements of the domain. So you could call it x. In the template, let me just bring up the template again. So in the template, it looked like this. You had a function from A to B. Give me two things in A, and you suppose that those two things have the same output. You do some work and show me that the inputs are the same. Okay. So down here, let's call the two inputs x and y. All right. So let x and y be integers. Okay. And then what we're going to do is we're going to suppose f of x is equal to f of y. All right. And what are you going to show? You want to show x is equal to y. Okay. So we get to make this assumption. Suppose f of x is equal to f of y. Well, what is f of x? We're given f of x is x cubed. Right? And what's f of y? Well, if the input is y now instead, if I replace this x with a y, that would be y cubed. Okay? So now we have this equation. Is there a way that I can manipulate that equation and effectively solve for x, and hopefully it'll be y? Well, what could I do to both sides of this equation? One thing you could attempt to do is you could take the cube root of both sides, right? So if I take the cube root, nice thing about cube root is you do not get multiple solutions for reals, right? So this would just be x, and this would just be y. Right? So I end up exactly with what I wanted. Okay, so you suppose that their cubes are the same, which means that they had to be the same originally. Okay, and that's it. So yes. So the answer is yes. Yes. F is an injection or one-to-one. And you could write it like that. You could write one-to-one like this. Okay. What about surjection? Okay, so let's explore that a little bit. Our template for this one, following our template, you pick something in the codomain. Okay. in the template, we called that B. So let B be in the codomain. I'm writing that here just to remind you that Z, for this function, Z was both the domain and the codomain, but down here I'm just making sure you realize that this thing is being taken from the codomain. I know that they're the same, I'm just trying to make you remember how the template actually works. So you pick something from the codomain, and now you're going to show me something from the domain gets mapped to it. So consider A equals something. All right. So what is this? So we go over here to some scrap paper. Oops. Okay. And what do we want? Okay, we want f of A to be equal to B. Okay. Because if I satisfy that condition, then I will have shown that if you give me something in the codomain, there's something in the domain that gets mapped to it. Okay, this is what we want. Well, what is f of A? F of A would be A cubed, right? So I want to solve, I'm trying to solve for A here, so I can substitute that. Well, if I can solve for A by taking the cube root, right, of both sides of this. So A would be the cube root of B. Now, normally what you do is if you solve for A, that's what you're going to substitute over here. Okay? But you have to ask yourself, is this always in A? The original domain. In that case, capital A is actually Z. Okay, so in other words, if you gave me an integer and then I take the cube root of it, is that always going to be an integer? If the answer is yes, then you'd be able to finish this, right? The rest of the template would just say, okay, calculate f of A, and that would actually give you B. You'd be done. But it looks like this is a problem, right? We have a problem, right? Can you think of an example where that fails? One example that I'm thinking of is, what if B was, say, 2? If B was 2, then the A that we would want would be the cube root of 2. And that's definitely not an integer, right? So if we have a problem, that means we probably have a counterexample. We might have a counterexample. And I think a good counterexample is exactly what we just said, right? So what that's kind of telling you is you kind of have to, stop this proof, which is your sort of standard proof, and now let's write out our counterexample. So we think f is not onto, or a surjection, and we'll provide a counterexample. So the proof for that. So, all this work is going to help us get this actual proof. So, in other words, we're kind of abandoning this, and that's perfectly okay. In mathematics, a lot of times you have to edit what you're doing. But all this work, it's not that it's useless. So it's not that you don't have to get rid of it. You could actually write this out, and you can clearly see we have a problem. We might have a counterexample. So now we're trying this sort of alternative proof. So you can consider any B that you want. So if B was equal to 2, then A would need to be A equals cube root of 2, which is not in integers, right? Maybe, you know what? Let me think of a better way to write that. Consider B equals 2. There is no A in the integers such that f of a is equal to 2. F of a is equal to this b here, right? Since f of a would be equal to 2, would imply a cubed is equal to 2, would imply a is equal to the cube root of 2, and that's not an integer. Okay, so there's no integer such that this is true, because if that were true, then you would have to force a to be the cube root of 2, and that's not an integer. Okay, so this is your counterexample to show that it's not onto. You found something that's an integer that's not in the range, right? There are some things that are definitely in the range. For example, if you pick a number that's a perfect cube. So for example, if you pick b equals 8, right, that is a perfect cube, right? 2 will map to that, right? 2 cubed is 8. So not everything is going to give you a counterexample. You kind of have to think about that a little bit. But some of this work kind of revealed that to us. Okay, so is f a bijection? Well, that's no. It's since f is not onto, right? Okay. Now, one thing that's kind of interesting to think about is there a way to fix this? All right. One way you could consider a fix is the real problem here is that the cube root of b was not an integer in general. Sometimes it is, but not in general. But what if you were dealing with real numbers instead? If b was a real number and not an integer, and you take the cube root of a real number, well then a would still be a real number. So maybe in that case it seems like it might be onto, right? If you actually had this same exact function, but for reals, okay? And that's exactly what the next question is. So if I just change the function just ever so slightly, so the only thing that I'm actually changing here is the domain and the codomain are now from real to real, and it's defined in the exact same way, then is it an injection and a surjection and a bijection? Well, the proof for the injection is exactly the same, okay? So exactly, whoops, don't quite know how that just happened. Okay, sorry, small technical problem there. So the proof of this is exactly the same as example 2 up above. Okay, nothing's going to change. The only thing that actually changed here is the domain and the codomain. So the rule is exactly the same. So well, I guess there's one small thing you would change. You would just say let x and y be real numbers. Okay, but then the rest of this work is exactly the same. So you'd set them equal to each other, you take the cube root, and they're the same. So, just let x and y be reals instead, right? So that's the domain, okay? And so the answer is yes, f is 1 to 1. Okay, and then is f a surjection? So onto. Well, here we're actually not going to have a problem. Okay, so the proof will actually be the continuation of what we did here. So let's write that out actually, so that way maybe it makes a little bit more sense. So proof. So let b be a real number, the codomain, in the codomain. Okay, so let b be in the codomain, and then consider a equals something. Well, we already solved that before on our scrap paper. Right? You will always want f of a to be equal to b. So on scrap paper, you kind of reverse engineer this. You're kind of forcing the situation. So what is f of a? Well, f of a, according to our rule, is going to be a cubed. Okay, so you effectively want a cubed to be equal to b. And now, can you solve for a? Well, yeah, I could take the cube root of both sides, and I get a is the cube root of b. Okay, so now you take this result from your scrap paper, you put it over here, And now you're just saying the following. Okay, it looks like it appeared out of nowhere. So when you're actually doing the proof, you're saying let b be a real number, and now let a be the cube root of b. Okay, well, what will happen? So now, what is f of a? Well, f of a will be the cube of this. Okay, so you take the cube of this, but what's the cube of the cube root of b? Well, that'll be b. And so you just forced the situation to be true. Okay. So you see how this scrap paper works? It sort of seems like you're cheating, but not really, because the way that existential part of the proof works is you just have to exhibit an example. So we can say, oh, well, I'm pulling this answer kind of out of my back pocket, and now it just happens to work, and that's perfectly fine. Okay, but just for organizational sake, you don't really want to have this as part of your proof, because you see that you're kind of assuming what you wanted to prove, and you can kind of do that off to the side, but not as part of the actual proof. Yeah. So the answer is yes, right? So yes, f is onto. Okay. So by fixing the function a little bit, we end up with something that's both one-to-one and onto. So the answer is yes. F is a bijection. Okay, what about this function? So this function takes elements from the integers, and it will give you an answer from the non-negative integers. So 0, 1, 2, and so on. So non-negative integers. Okay, and the way that we're going to define it is you're just going to take the absolute value of x. Okay, so is this function an injection? Okay, well, to be an injection, right, you have to, you could try to follow the template, right? So you could try the template. Okay, so proof, let x and y be in the domain, and then you're going to suppose f of x is equal to f of y. And then you want to show x is equal to y. Okay. So this is just following the template. So what is f of x? Well, f of x is absolute value of x. What's f of y? That would be absolute value of y. And now you're trying to show that x is equal to y. Well, does this imply x is equal to y? If the answer is yes, if you're able to show that, then you'll be done, right? And then that would show that the function is an injection. But if you stare at that a little bit, it looks like we're going to be able to come up with a counterexample, right? Because can you think of two integers whose absolute value is the same, but they're not the same? Well, yeah, there's lots of them, right? So does this imply x is equal to y? No. Consider x is equal to plus 1 and y is equal to minus 1, right? Then absolute value of x is plus 1 and absolute value of y is plus 1, right? If I take the absolute value, both of these are the same. So absolute value of x is equal to absolute value of y, but x is not equal to y. Okay? So this right here shows you, so this is a counterexample, right? So this proves proof that f is not one-to-one. Okay? So see, following the template, if you get to the point where you know that there's a problem, then it's not that it's useless, it's just telling you that, oh, maybe there's actually a counterexample to this situation. Okay, so yeah. Okay, so it's not one-to-one. What about onto? So is this function a surjection? Okay, well, to be a surjection, then you have to be able to exhibit something from the domain that is always going to hit everything in the codomain. So if you kind of look at the codomain, when you take absolute values of integers, you're going to get answers that are in this set. So it seems likely that this will be onto, right? The absolute value of 0 is 0. The absolute value of 1 and minus 1 is both 1. The absolute value of 2 and minus 2 is 2. You see that you're always able to find something that hits everything in this codomain. So we could try to prove it using the template, right? So try the template. Okay, so prove let B be an element of this set. So B is greater than or equal to 0 and integer. Right? This is the codomain. Okay. Now think about this. So consider A equals what? All right. You want to show that you can find, you don't want to overcomplicate this, but effectively what we want to be able to do is this. Looking at the template, I want you to be able to fill in this blank, and I want to be able to get B, right? So I want to find something that maps to B under this function. Well, but what is this function? This function is just taking the absolute value. So if I hand you an integer that's greater than or equal to 0, okay, so for example 5, can you think of something whose absolute value is 5? Sure, right? 5 works, but also -5 works. So do you see that for this one I don't really have to do any scrap work? I can just say consider A is equal to B. Okay, this is definitely still an integer, right? If B is in this set, then B is definitely an integer, right? We said that it was an integer, but also greater than or equal to 0. And if I slowly try to evaluate this, what is f of B? Well, that would be the absolute value of B. And the absolute value of B is B because B was already in this set, right? B was greater than or equal to 0. So I don't have to do like a sign switch or anything like that. So I'm done, right? Now, you could do some of this scrap paper work, but you're going to see really quickly that it's kind of silly sometimes to actually do this work, right? You want f of A to equal B. What's f of A? Well, I want the absolute value of A to be B. So this actually presents two solutions. So either A is equal to B or A is equal to minus B. Okay. Now this solution is not, well, actually, no, either one works. Both of these are legitimate answers, because if you said A was B, that's exactly what we did over here. But if you pick negative B, that's still an integer. And then the absolute value of negative B would be positive B. So actually, you have multiple ways you could get this answer, right? Okay, so the answer after doing all this is yes. F is onto. Right? Just looking back at the function real quick, you're taking the absolute value. So do you agree that everything over here is a possible answer to an absolute value? Well, yes. These are the non-negative integers. If I included a negative integer, that would be a problem, right? If it was, say, from z to z instead, then it would definitely not be onto, because, for example, I can't find an integer whose absolute value is -1, right? So I need to be non-negatives to guarantee this this onto part. So it was not 1-to-1, but it was onto. So that means it's not a bijection, right? It has to be both. Okay, and then finally let's look at this function. So over here, let's say that f maps z to z It's defined by taking the fourth power instead of the cube. Okay, so is f an injection, 1 to 1? All right, well, what I usually would suggest maybe doing is on some scrap paper. Might not be a bad idea to actually just think about the function a little bit. Sometimes you can jump right to the template and try doing that, right? It looks like I would be taking fourth roots, but taking fourth roots is going to be a little bit complicated because that will introduce plus and minus solutions. Okay, so if you do follow the template, it might hint that there might be a counterexample. But start to think about this a little bit, just like we did with the absolute value. If I give you some integers and you take their fourth power, are there two integers who have the same fourth power? Right? So the short solution of this, right, is no, it's not. Okay, it's not an injection. For example, consider x equals 2 and y equals minus 2. Okay, well, f of x, what's f of 2? F of 2 would be 2 to the fourth, which is 16, right? And what about f of minus 2? F of minus 2 will be minus 2 to the fourth, which is also 16. So they had the same output, but these inputs are different, right? 2 is not equal to negative 2. So that means that the function is not an injection. Okay, so I just wanted you to kind of see that right from the get-go. Sometimes you can just play with the examples a little bit and realize it's going to fail maybe the injection or the surjection part, the one-to-one or onto. You could get that by also trying out the template real quick. Like if we tried the template, let me show you where that fails. You would write proof. Well, it's not really going to be a proof because we already know that it's going to fail, right? You would say suppose x and y are integers, and suppose f of x is equal to f of y. Well, that'll imply x to the fourth is equal to y to the fourth, and then the natural thing would be to try to take fourth roots, right? But when you take fourth roots of both sides, when I take the fourth root of x to the 4 and the fourth root of y to the fourth, this will not imply x is equal to y because I'll actually have multiple solutions here. Okay, you will not get x is equal to y. You'll have multiple solutions. Okay, that happens when you take even roots. For example, when you take the square root, remember how you actually get plus or minus the answers? With fourth roots, it's pretty similar. With odd powers, that doesn't happen. You're guaranteed that there will be, if we're talking about reals here, real numbers, then you'll be guaranteed that they are the same. Okay. And what about surjection? So surjection, if you want this function to be onto, is every integer hit. Well, when I take the fourth power, is that a problem? Well, just like taking the third power was a problem, it's the same with the fourth power, right? So for example, so this one, no. 2 is an element of z in the codomain. But 2 is not in the image of f, since if there were, or if there was an A integers such that f of a was equal to 2, then that would mean a to the fourth is equal to 2, and that would mean a is the fourth root of 2. But the fourth root of 2 is not an integer. Okay, so this is kind of the problem. So we could use the exact same approach that we did for the cube root one. Okay, so it's not, as long as you can find examples of things that are in the codomain that are not in the image, then you're perfectly fine. There are going to be some things in the image, right? Some things are actually hit, so those would be perfect. Instead of cubics, they'd be quartics, right? So perfect cube, perfect quartic, I guess you would say. So something that if you took the fourth root, you would actually get an integer. So for example, 16 would work, right? So if I took 16, that's in the codomain, and 2 would map to 16, right? Because 2 to the fourth would be 16. Okay, so there are some things that are hit, clearly, because this is a function, right? A non-trivial function. But it fails both of these, right? Okay, so the answer is no.